Okay, the first of several short presentations or videos on two-port networks. And in this first one, we're just going to talk about the impedance parameters. That would be like resistance parameters, Z parameters in the terminology. And we'll also discuss the Y parameters, the so-called admittance, that's the inverse. And then something called hybrid, which we need for just for a number of different things, especially transistors and semiconductors, these kinds of things. Okay, so here we are, and let's just take and begin with the definition of a port. We've got some linear network. Okay, now it is important that it's a linear network. It's not something that's, well, non-linear, something that's strange and can have random events in it and things of that nature. So when you take a linear network, we're used to resistor networks. We've done tons of these so far in E211 and 213. Standard stuff. So we do voltage dividers, we do mesh equations, so on and so forth. And often there is a source somewhere out here, attached here. So we apply a voltage and a current is forced in. Or we apply a current source and a voltage appears across the network. We call this item right here a port. So a port, and we need this because we're going to be talking about two-port networks. So a port is two pins, whoops, bad W, two terminals for voltage and current. Okay, it's like what you'd plug anything in. And by the way, you can have a plug like an iPad plug or an iPhone plug, and or a USB plug of any of the versions, USB 1, 2, 3, and you see all those pins, and you say, "Oh my goodness, that's not this kind of a port." Well, it is. If you actually dig into the definitions of what's going on in those pins, you'll find that they're actually pairs of pins define something. So even though like an iPhone charging cord has 8 pins or whatever the number is, or a USB 2 has 4 pins, that's actually 2 pairs of pins. So it's like 2 ports. Turns out one's a power port and one's a data port, but and so the network's inside. Okay, now it really doesn't matter whether the port is on the left or on the right, right? I can have a second device, which is a different device. Here I've got them labeled with a number 2. So, but it's still a port, okay? And what we're going to be interested in this chapter is merging 2 of these kinds of ports and making a single device with 2 ports. And they are generally thought of as input and output. So to make the picture nice, we'll talk about it here. And we can think of this on the left as in, and this on the right as out. Okay? Doesn't have to be that way. That's just my left and rightness. But it tends to be how things are drawn up and pictured, right? We read left to right. You get languages that progress right to left, and they might make their drawings different. I don't know. Okay, so basic terminology then of a port. Something that handles voltage and current, and there tends to be an input and an output. So now we're going to talk just in this remainder of the video about the impedance parameters. So this is like a template or a paradigm of what parameters are in characterizing two-port networks. So here's our network picture again. We've got two voltage devices, right, attached to each port and a current flowing into each port. So you could flip that around and put two on the left and one on the right. You can do the same thing using current sources instead of voltage sources, and that would be quite legitimate here for impedance parameters. These same things will appear for admittance parameters also, because they're just voltage or current sources. They are a source that you can apply or a meter that you can use to measure. Okay, either characterization, either picture results in this simple set of equations. Now these are vector equations, right? So the voltages here, that's why they're big and bold capital letters. These are vectors, and this is going to be, what, a complex number possibly. Z11, whatever that is. All this is indicating right now is there is something that is going to become, or we're going to refer to as impedance, and there's four of them. One that relates input current and voltage, right, Z11. This term relates this to this. Okay? So somehow those two are going to be related. And knowing Ohm's law, we're going to imagine, we're going to just think ahead. It's probably going to be something like this. Voltage divided by current. Okay, and Z12, this guy is going to relate this to the current on the output. So in the picture, it's going to relate this to this. All right, now we can do the same thing on the right-hand pair of terminals. And so Z21 is going to relate this voltage to that current. And this guy is going to relate that voltage to that current, okay? And all it says is, I'm going to be the relating term. Like here, Z21 is going to be V2 over I1. And you say, but wait a minute, Bob, there's all kinds of other terms in here. How does Z21 get so easily related to those two guys? You'll see that in a moment by how we define the impedance parameters. Okay? So in simple matrix notation, this is how that gets written. This down here is just a rewrite of this. Same thing. We're just writing it in matrix notation now, right? Where V1 is Z1 times I1 plus Z2, 1, 2 times I2. Okay, and if you really tighten it up, it looks like this. So these are the Z parameters that that we all think of. Okay. All right. So now we have. Let me just put up those simple equations, and you have these. But notice what we have. Each of the Z terms, the four terms, relates to, you can find it provided the output or the current from the opposite side is 0, right? In other words, what did I have here? I had let's just take this example. V1 is Z11 I1 plus what? Z12 I2. Okay? And I just simply said Z11 is V1 over I1. That's this thing right here. And that's true as long as I2 is 0. And likewise, I can find this guy by saying if I1 is 0, then the equation is left standing this way. right? So this is how we define or find the Z parameters, and they are, for this reason, called the open circuit parameters, because how do you get I1 equals 0 or I2 equals 0? You just open the terminal on the opposite side, okay? So they're called the open circuit parameters, and the four of them are defined as the open circuit input impedance. And I think you're going to find as we go along that you've already seen a lot of this in the form of simple resistor circuits that we've built and measured. And by the way, keep in mind now, this measurement technique, this way of viewing circuits also leads to measurement techniques that apply. So Z12 is referred to as the open circuit transfer impedance. So the key word here is transfer and input. 1,2 means there somehow is relating the output and the input. 1,1 is simply relating the input to the input current and input voltage. These you've typically measured, these are like the Thevenin equivalent resistances or impedances, right? So these are also referred to as the driving point impedances, and the others, the 1,2 and the 2,1, are the transfer impedances. So it's the same thing in reverse to the opposite side. Okay? So just some terminology there, but this idea that you you determine these Z parameters by open circuiting the opposite, the other terminal, right? Okay. Now, pictorially, we can show it like this, right? Pretty easy. If I want to determine Z11 here, right, where am I at? If I want to determine Z11 or Z21, right, the effect from 2 based on 1, I just disconnect that any source, or you don't even short circuit this. You just disconnect, open circuit the opposite port, the opposite pair of terminals. Okay, so now you can also imagine this is leading to a measurement technique. I just simply pull the wire out and then measure voltages, right? Or measure currents. If I want to find this one, say Z12, I look down here and it says, oh, open circuit this, I'll have my voltage number 2 on, and see what current I get, right? Or see what voltage I get over here, because I know the current I'm applying here. All right, we'll get into that, and we'll do some of that in lab. That all leads to the laboratory very well. Now, you might also see that, or ask that, what about if some of these resistances, or especially if the transfer impedances, are the same, right? See, it's kind of natural. If the resistances, these driving point ones, V1 over I1 and V2 over I2, because those are just a function of the values at that terminal, V1 over I1, V2 over I2. So that's going to give you, like I said, what we think of as a Thevenin impedance. But if those are the same, we call the circuit symmetrical, right? Similarly, if the transfer impedances are the same, in other words, if V2 related to I1 is the same as V1 related to I2, right, if those two are equal, then we call the circuit a reciprocal, because that's going to say what transfers is going to be the same. And I can test that by saying, if I put a voltage on one side or if I put a current on the output and measure the voltage on the input, I will get the same result if I put that current source on the input and measure voltage on the output. Right? So it's a way of flipping the circuit, and so so that's reciprocal in that the transfer impedances are the same, right? So the port-to-port transfer type function is the same, which means it's going to behave the same in both directions. Whereas symmetry means it's as though you have two equivalent Thevenin sources or two equivalent driving point impedances. Okay, so let's take a look at this now. Here's our equations, just to be had. So let's take let's consider what I just said about symmetry and reciprocity. Symmetrical, reciprocal would mean, right? So this is a reciprocal. Okay, so Z12 equals Z21, right? So you notice up here in this circuit, there is no Z21. It's been replaced by Z12. But more than that, what is going on here? Does this circuit represent these equations? Well, look what's happening. If I take the input loop, V1 is equal to Z11I1, here I've got that, plus Z12I2. What's going on here? I got minus Z12I1. Let's write what's happening here. So the voltage here is I1 times Z11 minus Z12. All right? The voltage here is what? Z12 times I1, plus I2. Okay, so now if I complete that loop, what is it I'm going to get? If I complete that loop, I've got V1 is equal to Z11 I1 minus Z12 I1 minus, did I write that right? Oh no, it's equal to Z11 minus that plus, I'm doing it as equal. I'm not writing this equal to 0. I'm saying this voltage is equal to the sum of these two voltages. So it's I1 times Z11 minus Z12 plus Z12 I1 plus Z12 I2. So let's clean that up. Is Z11 I1 minus Z11 I1 and plus this plus Z12 I2. Okay? Which is exactly this. This and this are the same. Okay, so somehow this equation represents this input loop. Well, sure, what happened is I just subtracted away that value right here. And I'm going to do the same thing on the other side, and I'll get the second equation. Okay, so this is for a reciprocal circuit. What does this mean? Let's say these were resistors. This means I could represent this pair of equations as a simple T equivalent circuit with resistor values of this amount. They don't even have to be resistors. They only have to be impedances in this amount. Okay, so as long as they're reciprocal, I can use this T equivalent and off I go. Okay, so the important thing about equivalent circuits here, but that requires that this guy and this guy be the same because I did a substitution there. If they're not, here is an equivalent circuit. So this is the general form. The general form of equivalent. Okay, and what does this mean? If these two are different, see now notice if this is Z12 and Z21 are the same, these two represent the same voltage and you can just add them. That's where we are back here with, but this is the general form. So this is a direct representation of these equations in circuit form. These equations can always be represented by that. All right. Now what is nice here is, look, you clearly identify the input port, you clearly identify an output port, and you have some kind of a transfer impedance. We represent it as a dependent source because it says what? The effect on V2 from the current on the input side is this, Z21 times that current. Okay, so this is a general form of a two-port network where we don't have reciprocity or symmetry, either one. And just as an aside, because it'll come up again, the transformer is a representation of a two-port network that has no Z parameters. Because look what we have here. We've got V1 and V2. They're related by turns, the number of turns of wire. And I1 and I2 are related by the number of turns of wire. So these equations here don't hold up. There's no Z params. Okay. A quickie. I'll take a couple of moments. I know this is going long, but let me put these up real quick and show you. I just grabbed one of the shorter practice problems. Here's this. So here's a terminal with a resistor and another resistor here, right? And these, now we recognize this. If we put a voltage source here and we measured voltage here, right? This is just a voltage divider. We know that. And I'm just going to pop in a couple of easy values, 8 ohms and 4 ohms, right? So let's just find the Z parameters real quickly, right? Remember, and I copied the equations because it's tempting to want to go do something else here, but let's not do that. Let's just use the equations. I2 is 0, so we can do both of these with I2 equals 0. Z1, 1. So I2, that's right here. I1. Right, I2 is 0, so that means nothing's connected over here. Z11 is V1. V1 divided by I1. But we know if there's no current here, the total resistance is 12 ohms. All right, and as long as we got I2 open circuited, let's do, so that's the driving point impedance. Whoa, not that. Let's do Z21, right? That's the output voltage, V2 over I1. So now here's where our voltage divider thing comes in. V2 is going to be 4 times I1, right? And then the equation says to divide it by I1. So that transfer impedance is 4 ohms. Okay? Now let's do it the other way, where we got Z12. Let's find the other transfer impedance. So that's V1 over I2 when I1 is 0. So we'll leave this open circuited. So I1 is 0. The voltage here, this is going to be the voltage. V1 is there's no drop across this 8 ohm resistor. So it's going to be 4 times I2 divided by I2, so also 4 ohms. So we see before we even finish, this is a reciprocal circuit. All right, and the final one, Z22, is equal to what? We're going to leave I1 open circuited, and we're going to be solving for V2 over I2. Right, and that also is going to be 4 times I2 over I2 is equal to 4 ohms also. Okay, so this is a way of characterizing a simple voltage divider network as a two-port network. Okay, and I deliberately picked this easy case because you have it, and you have a lot of others fully worked out in the text, but it just says, it lets you know you can do an awful lot of analysis that's going to hang together when you start attaching circuits together. I mean, what if, for instance, you wanted to start, you had a network, and this is that first network, and it's now number 1. And maybe this is what goes in there. But now you're going to go on and you attach some other network here. Right? Another network too. And maybe it's a different resistor network. So we could draw this as, maybe you've got this network. Right? And now in network 2, you've got something like a capacitor here and an inductor here. And look, and maybe you can even complicate it and put a resistor in there. But look, I can analyze it as 2 separate networks. That one I've already done. And now I can analyze this network. All right? We know we can make impedances for all of these. But now it's in the frequency domain. Okay? So I'll go with this, and the next one we'll take up will be admittance parameters.